So, welcome to all. We are back right from the break of the New Year's celebration, and happily, we could get together again. I see that everybody seems to be well. That's good. And I hope Stefanella is better too. We heard that she had some health problems. Um, but today we're honored and happy to have our colleague Joaquin Delgado from Mexico. Joaquin is a friend from some time already, right? Well, I remember him from a few decades ago, so that's a long way, and it's very nice to see him here with us. I'm very glad, and I'm glad to be the person who is introducing him to today, no? And Joaquin has collaborated with some people from Recife. I think, well, has visited Recife many times and has collaborated with people from here. And I see that he has been diversifying his research. He's now interacting with people in the black hole community and from the more advanced, I guess, people working with unification in physics. Well, so today we're going to have Professor Joaquin Delgado from Universidad Autónoma, Metropolitana, Iztapalapa-México, and he's going to talk about classical trajectories in the black hole revisited, corrections by loop quantum gravity. So thank you, Joaquin, and the microphone is all yours.
Thank you. I must confess that I'm a little bit nervous. It's not the same as talking face-to-face with my colleagues. And please let me beg your pardon because my slides are in Spanish. I didn't have time to make the proper translation to English because of the time. So what I want to talk to you is to present you some main ideas behind the computation of some geodesics in a black hole geometry and how these geodesics are corrected by one of the main theories that tries to quantize the gravity, which is loop quantum gravity. And this is joint work with Gabriela Sanchez, which is our master's student, and Hugo Morales-Departamento, which is a physicist. He's the specialist in these topics. And I appreciate very, very much his guidance through these topics, which are, I just recently been working with him. And also, I think the organizers, it's a pleasure and an honor for me to give this talk commemorating 8th birthday of Hildeberto Cabral, a very caro amigo de muchos años. And so let me give you this. This is the overview of my talk. It's the first part. I will remember you basic facts about geodesics and how the equations look like in some particular geometry, which is called the Schwarzschild geometry. And in the first part of this talk, I will revisit a famous paper by Yusuke Hagihara, which was an astronomer which published a complete solution of these equations using the Hamilton-Jacobi technique in terms of very specialized functions, which are called Weierstrass elliptic functions. I will present a particular orbit computed by his formulas. And the final conclusion of this first part is that after a very hard work revisiting this paper and making all the details, we found some corrections. Some of them are misprints, surely, but some particular solution is wrong. And it was very difficult for us to detect this error, because we have to compare with other solutions which are presented in the literature, as for example, Chandraserkhar. And we didn't see anything published about these mistakes or misprints. And I hope this will be useful for anybody who wants to retake this lecture of this famous paper. In the second part of the paper, I will give a very rapid overview on the general theory of relativity and some of the main ideas that are the conducting ideas through the quantization of gravity, mainly the theory by Asner, Arnowitz, Desser, and Misner. And then I will go very fast through some specialized variables introduced by Iztapalapa-México, and then I will retake the geodesics of the Schwarzschild geometry in the interior of the black hole, and we will see how the corrections from loop quantum gravity predict that a natural continuations of solutions that go into the singularity of the black hole at the origin to the solutions that eject from a white hole. A white hole is a mathematical solution of the Einstein's equations that exist as a mathematical object, but physicists don't think it can be a possible real scenario. Nevertheless, since we are studying the mathematical properties, I will present this kind of solution. And this is very related because to very classical work that goes back to Sundman, when he studied by analytic continuations solutions of the three-body problem that go to the singularity. So let me give a very fast review on the geodesic equations. We have a remaining metric which has this kind of signature. So it's a non-positive metric. There are several conventions. This is one of the conventions that Hagihara used in his paper. And on purpose, I will copy some of the parts of that paper in my discussion in the first part, because at the end I want to make explicit some solutions. So in the remaining geometry, you have a remaining metric or a pseudometric, and you compute from the geodesic the metric coefficients, you compute what are called the connection or Christoffel symbols, which are written in terms of the derivatives of the metric coefficients. And if you want to minimize the length of all possible curves that join two extreme points, then by elementarily variational calculus, you end up with these famous equations, which are the equations of the geodesics. Here I am using systematically the Einstein convention of repeated indices indicating summation. These coefficients are naturally functions of the coordinates in which the metric is written. And these are second order differential equations. One important thing is that you can use any parameter you want in this to parameterize these equations. But if at the end you fix the norm, the square norm of your of the velocity to a constant value, then you will be sure that the parameter that you use is proportional to the length parameter or to the proper time in the language of relativistic people. Well, I will talk on this paper by Hagihara, Yusuke Hagihara, a famous mathematician and astronomer, which made very strong contributions to celestial mechanics. He's very famous, especially for his 4 volumes on celestial mechanics. And I will discuss a little bit in detail the content of this paper on the theory of relativistic trajectories in a gravitational field by Schwarzschild. This is a very long content, and this is the content of the chapters of this or sections of this paper. I will just review the first part and mention the technique, which is the main topic that I want to stress. The Schwarzschild geometry is defined by this Riemannian metric. Here I will use in this first part the convention that the signature of the coefficients are plus, minus, 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 and this is evident in this expression. Here R, phi, and theta are the spherical coordinates. We usually use this convention that I am trying to point at the left of this picture. We usually use phi for the longitude and theta for the latitude. But in this part of the talk, I will use Hagihara convention, where phi represents the co-latitude and theta represents the longitude. So please be aware that I will be using this convention in this first part. And the method consists in defining a Lagrangian function in terms of the kinetic energy defined by the metric. And because you don't have any potential in principle, you can perform the Legendre transformation and compute the Hamiltonian, which is essentially the same Lagrangian, except that it is written in terms of positions and momenta. The theory of Hamilton-Jacobi equation states that from the Hamiltonian, if you look for these partial differential equations, in terms of this, you look for a solution of what is called a Hamilton-Jacobi principal function of the Hamilton-Jacobi equation. If you find a solution for this equation, then you can recover the solutions of the geodesic equations defined by the Lagrangian. And one of the best parts I found explained in a very simple way the content of the Hamilton-Jacobi theorem is this in an old treatise of analytic dynamics by Pars, which says the following. If you find what is called a complete solution of Hamilton partial differential equations in terms of the position, the n positions and n arbitrarily constants and the time, this is called a complete integral of the partial differential equations, then you can recover the solutions by solving this system of implicit equations. Let me explain briefly. Since S depends on Q and alphas, when you can apply if you can apply the implicit function theorem, then you can take out from these the positions and express it in them in terms of the parameters alpha and the time. So you have the positions in terms of the parameters and the time. If you go to the second equation and substitute for q, then you get the p's, the momenta, in terms of the positions, which are as functions of time and the parameters, and in terms of these new parameters stated in this theorem. So this is the method of Hamilton-Jacobi equation, which is very briefly explained in this book. And this is how it looks like, the Hamilton-Jacobi equation for the Schwarzschild metric. Here, W is the principal functions, and Hagihara looks for a solution in the form of separated variables depending on the time, the radius, and the angular variables. And because of the system is autonomous, you can take out the time, the parameter, with respect to which the solutions are looked for. And after this separation of variables, after introducing this potential, please note that this function of u, small u is the inverse of the radius. This is a cubic equation. This is a term of cubic order, a second order, linear order, and a constant. Then in terms of u, you can reduce the Hamilton's equation to these quadratures. So if you can integrate explicitly or implicitly these equations, then you will get the solutions for the geodesics. In the deduction of this system of equations, there appears three constants of motion, which are denoted here by h1, h2, and h3. This alpha is the parameter, which is 2 times the mass of the Schwarzschild mass at the center. So you have to integrate this equation. Unfortunately, these are not in separated form, written in a very classical form, but they can be integrated if you introduce what it's called the colatitude. In fact, what happens is that the orbit of the test particle will move in a plane which is at the inclination I with respect to the horizontal plane. And if you introduce this angle psi and this angle phi, which is called the latitude, then by a simple spherical trigonometry, you find this relation between these two angles and the inclination. The inclination is related to the constants of motion h2 and h1 by this formula at the top. Then in terms of this angle, then this part which appears in the second equation can be written simply as d psi over h1. So if you perform this change of variable, then you can separate the variables for u. Essentially, this is the reciprocal of the radius and the angle psi. So you have to integrate in order to obtain psi in terms of u. You have to integrate this equation, which is a cubic in the square root that appears in the denominator. And as you can imagine, or anybody that has been some experience with special functions, you will try to reduce this integral to an elliptic kind of function. And the way that Hagihara does is to get out of this second order term by making a shift in the variable u. So the right-hand side of this equation is written in this form, or equivalently in this form. If you make the substitution of half the angle of psi, and that I will call capital psi, then this equation has a more familiar form, which is called Weierstrass differential equation. The solution to this equation is called the Weierstrass elliptic P function. and is written in detail in this form. So after this small change of variable, your solution is written in a standard form of Weierstrass differential equation. A more familiar way to write down this cubic equation is in terms of these two parameters, which are called the invariants of the cubic, and they define the genus of the elliptic Riemann surface that defines the elliptic function. Another quantity that is very important for the analysis that follows is the discriminant of this third polynomial equation, of this polynomial of third order. So in summary, you have the solution for the radial part. Recall that x, small x, is essentially a shifted u, and u is the reciprocal of the radius. So you have essentially found the solution for the radial part in terms of the elliptic Weierstrass function. Explicitly, the reciprocal of the radius is written in this formula. So from this expression, you can have explicit you can take out the r in terms of psi by elementary substitution. And let me just recall, fix some notation. One defines, if you, in terms of the roots of the third order polynomial, one defines the period, the two periods of the elliptic functions by these two formulas. I will take this formula in the next slide. So I will. That's the reason why I mentioned this at this time. Now let's start by analyzing the singularities of this solution. The singularities are related to the singularities. I mean, let us define two constant values such that P of y equals -1/3, P of z equals 2/3. In general, these solutions for these constants could be complex or real. It depends on the conditions of the problem. But you can, one can show that you can always find solve these solutions. You can find the roots for these equations. And in terms of these solutions, we have that if P of y equals -1/3, let me explain this briefly by going back to the previous slide. Say if you fix the value of P to -1/3, then it cancels with this term and it gives you u equals 0. If r equals to alpha, then this is 1. 1 minus 1/3 is 2/3. So P of c equals 2/3 corresponds to r equals alpha. And these are very special values. For example, then for P of y equals -1/3, it corresponds to the to u equals infinity or to escape. C corresponds to u equals 1, which is named the horizon. And u equals infinity corresponds to r equals 0, and it corresponds to a pole of the Weierstrass functions. So we have located the singularities which corresponds to escape to the horizon of the singularity at the origin by these values of psi, which satisfy these equations in terms of the constants y and c. Of course, these equations are taking modulus the periods of the Weierstrass function. Please let me wait for a moment to get a glass of water. 1 minute, please. excuse me, I have to go for some, to drink some water or some coffee. Okay, so we have located the singularities of escape or the horizon of the singularity. Let me just recall some basic facts about the Weierstrass elliptic functions. The elliptic functions are holomorphic, doubly periodic functions of a complex variable with this condition of the periods, which mainly says that one is not the imaginary part of the other. And for any elliptic functions, you can define the lattice of periods, which are defined as the integral combination of the periods. The elliptic functions are either because they are holomorphic and periodic, the simplest singularities that they can have, because they have to have, otherwise they would be constant. The simplest ones are the ones that have a pole of second order, or they have two simple poles. And this makes a huge difference. The first one are the Weierstrass elliptic functions, and the second ones are the more familiar Jacobi elliptic functions. Weierstrass function is defined as 1 over c squared plus, here's a plus missing, plus this infinite sum over all the lattice of periods. In terms of this, the invariants of the Weierstrass elliptic functions are related to the periods by these two formulas. And together with the Weierstrass elliptic functions P, there exist two important functions, their cosines or their relatives, which are the zeta and the sigma functions defined by these two relationships. Well, in terms of this function, this is the complete solution given by Hagihara after a very clever use of properties of the Weierstrass elliptic functions P, sigma, and zeta. And this is the expression after some corrections by a factor of 2. This factor is missing in the paper by Hagihara, and this sign is also missing in that paper. But it looks like these are misprints. But after a very careful review, this is the right solution. And we checked this with the solution obtained by Chandraserkhar in another reference that I will mention later. Well, after this short detour, we will use then either the invariance of the Jacobi function or the first integrals h1, h2. I didn't say, but in what follows, I will take h1 equals to h2. So only two constants will remain present in what follows. And taking h1 equals to h2 simply means that the plane of the orbit is an equatorial plane. So there is no loss of generality in supposing that h1 equals h2. So we will just forget about h2 and remain only h1 and h3 as constants of motion. Hagihara introduces two kind of parameters, lambda and mu. What it means is that we can use either the parameters G2, G3, or the constants of motion H1, H3, or the parameters lambda and mu as a way of mapping the possible values that the polynomial and therefore the solutions, the roots can have, and determine the kind of solution. Here's the cubic expressed in terms of these new parameters, lambda, mu, and the variable x, which is a shift of u. And this is a picture of the discriminant. This cusp curve is precisely the locus of the discriminant equal to 0. In the interior region, there are real roots. There are no real roots in this. Excuse me. Let me let me go back. The cubic has always a real equation. Because it's a cubic. Yes, this is must be, say, a cubic. This exponent must be 3. There's an exponent 2 missing here, but I apologize for the error. So this is 3. This is 2, and this curve is the discriminant of this cubic. As a cubic has always a real root, there are two possibilities for the other roots. Either they are complex or they are real, and they can coincide along this boundary of this curved region, which is the discriminant equal to 1. In the paper by Hagihara, there are several regions that then describe some different types of motion. I must mention, just as a bypass, that the same technique is applied in the Lars book on the two fixed point problem, and it's very interesting to compare this method with the book that I mentioned for the two center problems in the plane. Here's the some possibilities for the cubic y in terms of x for this cubic, and for example, the possible positions that the test particle can have necessarily have a positive value of y. So, for example, if you take the case 1, which is the curve mark with the Roman number here, means that the possible motion of the test particle is in this part. Since x is a constant plus 1 over r, when x goes to infinity, we go to the singularity at the origin. Here, for example, is the possibility of bounded motion at some minimal radius and a maximal radius. So this kind of solution will give you solutions that projects in the positions in a ring of possible motion. I will not discuss the very rich type of solutions that can appear in these cases, but I will refer to the paper by Hagihara. I will just present a particular solution. Here I present the discriminant curve equal to 0, and I just take very particular numerical values. This is mu and this is lambda, and I took these particular values, and then I compute the numerical roots that I have to find. Excuse me. Excuse me. I take this particular solution. I find that y is purely imaginary, z is real, and since we have r as a function of psi and the angle in terms of psi, then we can just draw the curve, and it looks like this. This is the graph of r in terms of psi, capital psi, and the interpretation is as follows. This line corresponds to the horizon. This point corresponds to an apogee or apocenter. This corresponds to the singularity r equals 0. And here we are just describing the geometric solution. namely, what I want to say is that there's no physics here. This is only geometry, because I'm drawing the radius as a function of an angle. So if we draw this picture in the plane, it looks like this. For example, when we start here from the apocenter, we go to the horizon in this direction. Then we enter the interior of the horizon. We go to a singularity, and this naturally continues through this solution. Of course, this solution has to be interpreted in the right way. This solution has to be interpreted as an ejection collision of a white hole. When we draw the proper picture in the space-time diagram, which is the right one to see the physics, we will see that we will take that the test particles will take an infinite time for a very long faraway observer to go to the horizon. And this is the way that we do with our solution. When we draw the graph of the time in terms of our variable, the capital Psi, we obtain this solution. Here is a sum of this part, and this vertical line corresponds to the horizon. So you find that we find that in particular, the time as a function of Psi has a vertical asymptote at the value precisely of the horizon, which is Z. Also, we see that at the singularity, namely for Psi equals 0, we have a discontinuity, but at least numerically, we can verify that this is a Young discontinuity that can be removed by adding an arbitrary constant solution to match this value to this one. We start with the numerical solution, but then afterwards we found some analytic expressions for another kinds of solution, and we found the same phenomena as I am describing here. So if you would describe the imaginary part, we draw the imaginary part of the solution tau de psi, T of psi, we find that it remains constant in the interior of the horizon, and at the exterior of the horizons, differing by multiples of the period. This is very atypical, because you don't expect for a function of a complex variable, when you perform analytical continuation, for the imaginary part to remain constant, but that's what it happens. After we remove the singularity, the discontinuity at the origin, then we obtain a time which we call this a regularized time. And in terms of this, we can draw the proper space-time diagrams. Here, the horizontal is the radius, T is the time. We only draw two-dimensional pictures because the angle is well understood in terms of the previous orbits. So what it means is that at this point we are in the apocenter, and then it would take an infinite time to reach the horizon. Also, if you go backwards in time, you will take a very long time, an infinite time, to eject from the horizon. So the solution from the outside of the horizon and at the interior of the horizon are disconnected by this discontinuity. Physically, this will mean that for an observer which is at infinity, the observer will find that the test particle that goes into the horizon will take an infinite time. Nevertheless, if we use a proper time, namely a clock that the test particle takes with him, we will see that in fact it takes a finite time to enter the horizon and then enter into the singularity. This is the solution expressed in terms of the proper time of the length parameter. This part will correspond to the solution going into the singularity, and this part will correspond to a solution ejecting from the singularity, namely a white hole ejection solution. But a more geometrical description can be made in terms of these special coordinates that are called Kruskal coordinates. They are defined by this formula for the exterior of the horizon and by this formula for the interior of the horizon. And this is the way they look like. These two lines in orange correspond to the horizon. And this solution starts from some point, maybe in the apocenter, then goes into the horizon and goes transversally through the horizon, ending in the singularity. The singularity now is described by this branch of hyperbola. And then from this goes the other part that continues the solution that goes to the singularity. In fact, what one has to do more properly is to make an identification of this solution with this symmetric solution. In this diagram, I must say that this part of the solution corresponds to the black hole solution, and this part of the solution corresponds to the white hole solution. So this is the way that we look at this solution, this globally continued solution in the Kruskal diagrams. Now, this ends the first part of my talk. Let me go very briefly to the second part, and I will talk very briefly about the main ideas in general relativity. In general relativity, we are interested in how the mass determines the geometry of the space-time. And we will must say more correctly how the energy momentum tensor determines the derivatives of second order of the metric, which are contained in what is called the tensor Einstein tensor, written in terms of the Ricci scalar and the Riemann curvature tensor, which is written in terms of the derivatives of the connections, which are derivatives of the coefficients. So this is a partial differential equation. Lambda is called it's a special, sometimes this is taken as 0. I don't remember the name. This is called, doesn't matter. So in the Einstein equations are partial differential equations that usually are takes the energy momentum tensor as the source, and you want to determine the properties or the coefficients of your metric. One way to derive the Einstein equation is through the Einstein-Hilbert variational principle. When you take the Riemann scalar, the determinant of the minus the square root of the minus the determinant, and then you perform variations with respect to the metric coefficients. When you do this, then it's a very standard computation to show that you in fact recover Einstein equations. Nevertheless, this variational approach is very fruitful because you can consider, or some people have been considering, other extensions of this variational principle. For example, Palatini considers the connection coefficients as independent variables of the metric coefficients, which are written symbolically in this way. And we can you can perform the variations with respect to the connection coefficients and to the metric. And what you find is that when you perform the variation with respect to the connections, you find the relations between the connections associated to a non-torsion metric. And when you perform the variation with respect to the metric coefficients, then you recover Einstein equation. So this principle of Palatini, even it looks like more general, is more or less equivalent to the Einstein-Hilbert equation, but it presents, historically at least, it motivated a lot of alternative formulations of general relativity. One of them is due to Cartan, what is called Einstein-Cartan formulation. Instead of the metric coefficients, one uses frames, orthogonal frames. In 4 dimensions, they are called Vierbein, which means four arms, orthogonal arms. But if instead of the metric connections, you use the an orthogonal frame as a variable to describe the geometry, then you have to admit some group of symmetries. In this case, the transformations that preserve the metric in each tangent space, which is SO13. This is the set of matrices that preserve a metric or a scalar product of signature -1, minus plus plus plus, for example. And this, in turn, conduces to a more abstract formulations in terms of principal bundles, where the symmetry group acts not on a manifold, but in a frame bundle, for example. And it has a very fruitful generalizations to other kind of theories. One point that is important here is that if you consider this gauge freedom, then at some time you want to compute derivatives of as you do with connections, of quantities that take values in the Lie algebra of this group. So at some time you have to consider, instead of classical connections, what are called spin connections. And this is very fruitful, as we will see later. One of the main contribution in this direction is what is called the Arnold-Desser-Misner theory, ADM, in which the space-time is foliated by, let's say, by a foliation of space-like three-dimensional hypersurface that we can imagine that are flow through a normal direction which corresponds to some time. This is strictly just a foliation of space-time in terms of leaves that are at all time space-like and have a normal which is time-like. This hypothesis of admitting a such foliation, in fact, is related to what is called global hyperbolicity, which has been exploited by a lot of people in the last years to show that the equations of the Einstein equations are well posed, and there are also existing theorems due to Linear-Owens, Fisher, Martin, Choquet-Puhaut, etc. Well, when we admit this hyperbolic structure, namely these foliations, then we can decompose the metric in some parts that are tangent to the three-dimensional hypersurfaces, and some other mixed components. Here we have introduced these quantities which are called the laps and the shift, and the metric coefficients that are really three-dimensional at each, but depend on time, of course. This is a nice picture from Misner and Wheeler book. When you look your space-time as supported by this kind of structure of hypersurfaces, when you have the liberty to, when you move a variation of the coordinates, for example, you have the liberty to move, the freedom to move along the surface and then normally to it, which is precisely this decomposition. Well, in terms of this decomposition, we can express the Einstein-Hilbert formula in terms of three-dimensional quantities, which are the scalar curvature for the three-dimensional hypersurfaces and the extrinsic curvature. This must be, say, extrinsic curvature. And from this, you can, what ADM theory does is to use Q, the coefficients of the three-dimensional metrics, the shift and the lapse as the configuration variables. And then one can see that all the quantities that are expressed here are in fact functions of these variables and some of the derivatives, derivatives of the Q of the metric. And one important thing is that it doesn't depend explicitly on the time derivatives of the lapse and the shifts. This has a very important consequence when you compute using Legendre transformation, the momenta. You don't have problem when you compute the momenta associated to the derivatives of the coefficients of the three-dimensional metrics. But when you derive with respect to n or n dot a, you find 0. So it means that you have a system with constraints. This is very well known and very well studied in what is called Dirac theory of constraint systems. And also there is a theory developed by Dirac where these constraint Hamiltonians can be quantized by well-known recipes or methods. In the third part, in the last part of my talk, I just mentioned very briefly that a very a profound contribution by Iztapalapa was the introduction of some kind of connections which are more general than the previous ones, and are precisely spin connections defined by these coefficients A, I, A, and these matrices which are essentially generators of SU2 group. I just recall that SU2 is the special unitary of 2x2 matrices with determinant equals to 1, and it's in some way associated to the SO3 group. Iztapalapa introduces then these coefficients, which are the spin connections, and these quantities which are the analog to the 3-vine or the three-dimensional orthonormal frames in the three-dimensional hypersurfaces, but which are densitized. This means that they are multiplied by the determinant of the three-dimensional metric. There's a relationship between this is an explicit expression for these coefficients, and we can enumerate from the symplectic structure in the space of connections and densitized frames by integration. We get as a reduction symplectic structure containing this famous parameter, which is called Barbero-Immirzi parameter. So in the case of our Schwarzschild metric, we can go from the exterior, this must say, excuse me, this must say R greater than 2m. This is the Schwarzschild metric. We can extend this metric to the interior because, as we have said, the horizon, which corresponds to R equals to 2m, or alpha, as we said before, is a singularity that can be removed by proper choice of coordinates, namely Kruskal coordinates. So we can continue naturally from the exterior to the interior of the Schwarzschild metric, and we can introduce this excuse me, let me go back. This metric, in order to emphasize that we are in the interior of the black hole, what happens is that the R coordinates, which is space-like, now behaves like a time variable. And the time variable now behaves as a position variable. So this is the, and note also that there's a change in the signature of the signs of the coefficients in the interior, from the exterior to the interior. And this is an example of a completely symmetric, under this group of symmetry, of a more general kind of metric which are called Kantowski-Sachs metrics, of which this is a special form. In terms of the Ashtekar variables, we can recover these coefficients in terms of the variables which we call PC, PB, and etc. Let me just go back a moment for this to this slide. These variables PC, PB are written here on purpose because they will be the momentum variables for a Hamiltonian system that I will talk a little bit ahead. Now, if we choose the lapse this way, this is a special election, then the Hamiltonian system, the variables, I will call the dynamic variables, PC, PB, C, and B, satisfy a Hamiltonian system, which has a very simple form and is derived by this from this Hamiltonian. And from these explicit solutions, we can go back to the metric and express the metric in terms of the original variables theta, phi, and the new time, which is the parameter of the Hamiltonian system that we have here. So we can pose again the same problem. We have just written our metric in terms of new variables, which are surrogated to a Hamiltonian system, which is generated for the global one, as ADM theory shows. So we can start again, and then from this we can construct the Lagrangian, then the equations for the geodesics, and try to integrate. If we perform these steps, we find that the equations for phi and x can be integrated to lower the order of the differential equation. And for the t variable, we have a more complicated equation. These are the equations of the geodesics in this in these variables. And this is a comparison, or this is a picture of what happens when we solve this equation. This is the solution for capital T in terms of the independent variable psi. And because we have a way to go from the solution to the original variable that we call tau, this is tau, then we can recover the previous solution that we had according to Hagihara theory. Here at the left is drawn the solution obtained by numerical integration of the last equations. This is the solution obtained by the analytic solution by Hagihara, and we see that they perfectly agree. We did this for a very numerical particle, for a particular numerical value of mu or lambda, but we also studied this for some other kind of analytic solutions that we have computed but not shown in this exposition. Well, in the final part, I will just mention very briefly what one does in quantization by loop quantum technique. Let's say that if you have since we have a Hamiltonian system in these reduced variables, and we have a theory of constraints in according to Dirac, we could try to quantize following the recipes. Nevertheless, in quantum loop quantum gravity, this is not the way, but the way is to propose a discrete model of space and time and perform what is called the integration of the connection along elementary loops of this discretized space and time. And after this is done, we end up with an effective Hamiltonian system, which is surrogated to our geodesics. And this is the lection of the, as we did previously, this is the lection of the labs, and this is the new effective Hamiltonian, where you see these two parameters, delta C, delta B, which are how is say the as pegadas, how do you say the trails of the process of quantization. So we can then compute the Hamiltonian system associated to this effective Hamiltonian, and then go again with the same method to compute the geodesics equation with this correction. And this is what we found. Let me compare first. This is this we will call the energy surface in the plane T prime in the language of celestial mechanicist, which is a closed curve. In the classical case, it's not a compact curve. In the classical case, we had that the solution goes to infinity. Instead, in the effective case, we have this this behavior. Now, what does it mean in the trajectories? What this means is that the solutions now with the correction by loop quantum gravity goes like this. Let's say that it goes from some apocenter, then enters into the horizon of the black hole, goes to a minimal distance to the origin, and then goes into solution of a black hole and goes out from the horizon of the black hole. Here is a sum of this small zone. When you see that this kind of bouncing in this circle, which really corresponds to a transition hypersurface in space and time. So this is the end of my talk, and I appreciate very much your time. If you have any questions or comments, I will be glad to. Annette, I just sent you my presentation previously, and I will be glad if you can share it in the page wave in case anyone can look at this in the details. I don't.
Everyone can please. You can repeat, Joaquin, please.
Oh, sorry. Yes, we can see her. We can see each other, right? Yes. I thank you. I was just saying that I sent the presentation to Annette. If you want to see the details in the presentation, I will be glad to send it to you if you want.
Sorry, I was disconnected. I'm back. Thank you, Joaquin, very much for your talk. Well, a little late.
It's a pleasure to honor.
Thank you. And are you answering questions already? Has anybody asked a question? No, not yet, right? Would anybody like to ask Joaquin a question? Okay, well, then we can take Joaquin again.
Thank you very much. I'm very happy to see you all. Take care.
Sorry, Joaquin, what you're saying?
I'm very happy to see you all again, and please take care.
Okay, thank you very much.
Thank you.
I don't know if you. I guess I know that guy. Okay, should I? Sorry, I'm gonna hide here. Okay, Ned. So you are in control again, right?
Come on, what can you say? Yeah, we can start the video.
Oh, okay. Go ahead. Good morning to all. It's a pleasure for me to be here to share with you this video. Especially to Hildeberto, it's an honor for me to participate in this homage to his life and works. I would like to say first and foremost, happy birthday, Hildeberto. It's very nice to arrive at your age and have a nice history behind and interesting perspectives ahead. Well, let me tell you how I met Hildeberto. First, I was still an undergraduate student in physics, and at the time I had taken a class in classical mechanics and physics, and it was pretty hard for me. And also, I was taking classes in math and thinking about changing majors. So it was nice that to know that Hildeberto was around and his area was celestial mechanics. So I ended up really not changing majors, but as soon as I finished physics, I started a master's in math. And Hildeberto was an important part of that decision. When I came from physics, I was actually a holder of a fellowship called Scientific Initiation from the Brazilian government. And it's sad to know that now, to tell you that now this fellowship is under threats and suffering cuts by the current government. Anyways, Hildeberto, I asked Hildeberto if he could continue the fellowship with me to the end of in the last semester of my of my undergraduate studies, and he agreed. And he assigned to me the 7th chapter of Hirsch's book on ODEs, which was interesting because I very, very quickly realized that my background in analysis wasn't good enough for that. So I ended up studying more analysis and stopped the ODEs project. But anyways, that was important for me. Then a few months later, I started the master's program in the math department. And then my first semester, I took multivariate analysis, of course, and complex variables. And Hildeberto suggested I take his ODEs class. Well, that was a very interesting class, I should tell you. And I was very impressed, must say, because besides the basic course, which I think was very influenced by the book by Coddington and Levinson, I don't know, maybe I'm wrong, but as far as I can remember, there was that influence. And Hildeberto had his own notes on some of the material. We also used Sotomayor's book. But what really impressed me was the additional material that he covered. We had 6 hours of classes per week, and 2 hours were dedicated to special topics. And many of them came from the Ziegler-Moser's book. And also, I believe, from the appendices of Arnold's book on classical mechanics. So that was really interesting. Around that time, Hildeberto's visitors program was happening, or starting to happen, I think, picking up more momentum. And I recall that I had a chance of attending lectures or short-term courses by professors Don Sari, Clark Robinson, Ken Mayer, many others, some from Mexico, like Ernesto Perez Chavela, Joaquin Delgado, from Spain, Professor Jaume Libre, from France, Alain Bouy, well, many others, sorry for the omissions. And Alain Bouy especially was interesting because at the time, I think it was around 1992, 1993, he was spending several months in Recife. And Hildeberto suggested that I ask him to be my master's dissertation advisor. Well, I talked to him, and we started working, sorry. But then I remember the difficulties I had in some of my background, technical background in math wasn't good enough to follow along. Actually, I really had a hard time following him, even though his Portuguese was quite okay, I would say, at the time. But I don't know, maybe also he was very young. And so anyways, I really liked the interaction with him, but I could not follow him. It's just plainly like that. And after some time, I was beginning to get worried about the dissertation, how it was going to go. And I talked to Hildeberto, and he gave me the paper by Devani, the paper that the one on the isosceles three-body problem, triple collisions, and the isosceles three-body problem, and excellent paper by Steele. It's one of my favorites. To this day, and I studied that paper carefully, and I basically could understand everything except some minor points that I asked Hildeberto to help. helped me with. And pretty much I wrote the whole dissertation, basically by myself on this. And then even had the chance of going back to a paper that came before that by Professor McGee from Minnesota, which I think started this whole area of blowing up triple collisions in exploiting what happens in neighborhoods of in the neighborhood of such events. So that was really nice, and I gained a lot of confidence in that work. And then I went back to Alain and actually managed to understand some of what he was doing. And I added one more chapter in my dissertation discussing that. So I was really happy with that. Well, then came the time to start planning for the PhD, and I decided to try the US, especially Minnesota. And I told Hildeberto about that, and he was very supportive. He wrote to Professor McGee about me. It was very nice, and the message, the email was very well received by Professor McGee, and he sent me the documents to apply. So everything worked nicely, and I left Brazil in August 1995. I was around out away from Brazil, basically until mid-2002. And when I finally came back, well, that was around that time, second semester of 2002. And in 2005, we have the first Matemairacorana, this event that, is of which the current event is a continuation, it's a follow-up. And so that was nice. I had the chance to meet again many other researchers, right? Well known. So some of them, Mark Levy, I remember very well interacting with him and attending his lectures. David Sozan and others. Sorry for the omissions. And a few, I think around that time, yes, that time Hildeberto had already retired. And yeah, so that's it. I once again want to congratulate Hildeberto for the achievement of this nice career, and wish him much success in the future. And I thank you very much for the attention and apologize for the long video. Okay, I hope all are well and remain healthy. Goodbye. Wow, that was really long. Thank you for your patience. Well, and thank you all again. It was nice to meet you all. I think pretty much all of you I met through Hildeberto, so thank you. Thank you for that.
A nice presentation, Eduardo.
Oh my gosh, don't say that. Next time it's going to be twice as long.
A little bit of history is always interesting.
Okay.
Nice presentation. Right. I really enjoyed that, and hopefully we'll see each other soon. Okay?
All right. Well, now can I finally transfer to you the command of the ceremony? So, do you want to say a few words for the, for today and for next time? Annette?
So, no, I think that we can stop to recording and take the official picture from today. And